All right, Luke, we're back in a new place with some better audio. And today we're going to be talking about an introduction to battery system voltage. We'll go over things like what the difference is between a high voltage and a low voltage battery system, why certain vehicles and stationary energy storage systems are being designed to a higher voltage, what are some design considerations when choosing your voltage for your battery systems, and then we'll talk about what we consider an ideal battery system. Are you ready for today, Luke? Yeah? All right. So the first thing we have to talk about is battery capacity. How is it measured when watt hours, kilowatt hours, megawatt hours? What do you calculate that from?
The nominal voltage of the cell times the capacity of the cell coulombically. And this nominal voltage is the average voltage it's at as it's expending the energy across the discharge capacity of the cell. And so the nominal voltage actually depends on the use range for the application. It will drift slightly depending on how high of a voltage you charge to. And so those, the product of those numbers multiplied gives you watt hours, as a watt is an amp times a volt, and then in capacity, a watt hour would be the ability to deliver a watt for an hour. And so these have a relationship, a multiplicative relationship with watts between amps and volts nominal capacity.
Cool.
Yeah.
So in consideration of the conversation today, I think that we've talked about 150 volts DC being kind of that borderline between what we would consider a high voltage system and a low voltage system for batteries.
Yep. There tends to be a no man's land between a little below 150 and a little, it doesn't start having systems designed again until around 300 volts or so. And so there's this gap in which silicon MOSFET controller devices and IGBT devices are both poorly suited in that gap. So the IGBT is poorly suited because the percentage of its forward voltage drop, it has a pair of 1.7 volt diodes in series for 3.4 volts of drop. So if you're running a system at 100 volts with IGBTs, then you've got 3.4 volt percentage loss at all loads. Even if you're just at a light cruise load, you're eating this significant percentage loss. And for this reason, you don't see IGBTs used until say 300 volts, 350 volts, let's say, because around that range it becomes only a 1% loss. And in a MOSFET, you have just something they call RDS, on, or resistance between drain to source, in the on state with the gate. And this means resistance can approach zero in a MOSFET from the aspect that, let's say that you're at cruise loads, there'll be roughly no voltage drop across the MOSFET at these lighter current loads. And then as you go into heavy current loads, there won't be some fixed tax in forward voltage. They'll just be proportional heating to the amount of current you're pulling. So
that's why you don't see a lot of 250 volt vehicles. You see either
right.
48 or 110, and then 300 is really the next spot.
Yep. From a silicon switching perspective, 100 volt switching parts and 150 volt switching parts are very similar in the amount of power they can switch per device for a given amount of losses. And so we'll talk about it in a few minutes, but one of those options has a lower cost, and there's some exceptions to that as well, though. But
so a lot of the big misconceptions we get when we talk about why a certain person might have chosen a system voltage is the V equals IR equation that most people learn in their physics courses.
Yep.
Are there any common misconceptions that kind of come up to clarify?
There's one huge one that we see all the time, and it's I need this voltage so that my X, Y, or Z performs well. And that's, man, there's a lot of reasons why this is easily to confuse people, but essentially, if the device that they're powering is, say, a motor, for example, or really any type of electromagnetic device, solenoid coil or anything, it's the percentage of copper fill that they can get into that slot that will determine efficiency, continuous power, torque, continuous torque, saturation torque, losses, efficiency. All of this will be determined by the percentage of that slot they can fill. Whether the slot was filled with 100 single strands of fine wire, or one strand that was 100 times the size, or a bundle of 100 strands, whatever. It's an identical electromagnetic model in the slot, and it's an identical, if you were to take slices of that wound motor stator at any point, you would find whether you did a 10-turn winding with 10 amps on it, a 1-turn winding with 100 amps on it, or a very fine wire that you wrapped 100 times around it and put 1 amp on it. If you took slices there and looked at the current density through the copper, you would say, they're all, exactly identical models of each other. And the proportional electromagnetic field it generates is also exactly identical. And the losses it generates is exactly identical. The places where it changes,
there's quality too, right? If you're crimping, 100 wires versus one.
Let's get into one more aspect of why they're the same, because people are often confused by the I squared R, and they see this square on current and they go, oh my gosh, I know if I have a square somewhere, things get out of hand quickly, right? So the reason why they're all identical resistive losses, identical heating, despite one operating at 1 amp, one operating 10 amps, one operating at 100 amps in that previous example, you'd think, the 100 amp one, it's 100 amps times 100 for 10,000, right, in the equation, times resistance. And that's all true. And in the 1 amp one, it's just 1 amp times 1 instead of 100 amps times 100. The difference, though, is that one of them is 10,000 times higher resistance than the other, in that particular scale example. And so everything balances out to be zero sum. That the 10 turns with a 10 time thicker winding, it's because when you go to a fatter winding with fewer turns, you get thicker at the same time you get shorter, because the total series path it had to take looping the tooth is reduced. And so because you have this square root function of resistance dropping as you get shorter and the bundle gets fatter, it ends up being a zero sum game, in electromagnetic device performance. So if a battery pack is an arrangement of cells, and so as long as you're not trying to get below the 3.7 volt, nominal building block of one cell group, right, then you can just adjust. You needed some quantity of cells for some amount of energy, and you can now just arrange them in a series group to be, the desired voltage. So the battery pack itself is, completely agnostic to the configuration in which the cells are configured. And the motor is completely agnostic into the pattern of wires you choose to complete filling those slots with, provided you have the amount of copper fill in the slot at the same percentage. You'll have the same performance between different winds. And so what this leaves is your motor controller is really the factor for determining what voltage makes sense for your system, designing around the limitations of the switches in the controller and the capacitors in the controller, and that, the power regulation stage and filtering stage. If you have 150 volt parts, you can't just run at 150 volts. You have to run at around, say, 120 volts peak, because in these high dynamic transient conditions, it's common to see spikes of, say, 15, 20, 25 volts. And so it's critical to leave margin so that you don't damage your switching electronics.
So that kind of gets into the next section we wanted to talk about, which is designs of different battery systems according to voltage. And one of the things we wanted to cover was the availability of powertrain products. So you've been talking about the motor, and then you kind of hinted at the motor controller, and
Okay,
a lot of the larger EVs and things like that.
I'm ready to get into that.
Sure.
You'll notice for off-the-shelf high-voltage products, it's incredibly limited options. Every EV that's on the road is not buying someone's motor controller. They built their own in-house. Every EV on the road, there's probably some exceptions to this, but just about every EV on the road that runs high voltage made their own DC-DC converters, made their own, charging electronics, obviously their own battery management systems. And if you're going to integrate at that level, then component availability doesn't really matter because you're going to build all your own components anyways.
But if you're an integrator,
that's right.
Like
if you're an integrator,
like if you just make battery packs and somebody else makes the trucks.
If you're an integrator, then
or cars,
and you want something high voltage, you're limited to using a handful of offerings, and we could count them on one hand probably, of course. And some of the offerings are very price prohibitive because they're kind of racing specific boutique products, and. If
availability of powertrain products is not really an issue in scale, right? Once you're designing all of your own electronics, but as far as like doing prototypes and things like that, it's very difficult.
It's very difficult. And from the aspect of, let's say even in volume, let's say you need things like fuses, and your arc flash energy gets nuts, and your arc breaking energy and quenching plasma, when you have an arc fault, like a fuse element clearing, which is a type of arc fault inside a fuse. When this occurs, the higher the voltage, the longer you can sustain this energy for, and for example, many fuses that had high voltage ratings in DC, end up getting derated because they were tested with equipment that doesn't have batteries current delivery rates, but the current delivery rates on batteries is like almost instantaneous. Like what's your inductance? Like approaching, your equipment can't measure it, so tiny, right? And so the current rise rate is approaching a step function towards, many kiloamps or tens of kiloamps, depending on the pack size. And this means the challenge of splitting these plasma joints, in conductivity when the element shears gets to be crazy. And this is why there's things like pyro fuses. It's also the soft short circuit potential too. Low impedance busing, lower voltage systems, can clear fuse elements without drawing an arc for a long period of time, and open contactors under load without destroying as well. Obviously there's a threshold where everything breaks, but they have a much more generous tolerance window at lower voltages. So even if you're, say, Tesla, you still have to deal with the high voltage challenges in every component and every connector choice, and the expense that goes along with that, and life safety touch protection as well.
Right. Another one of the common arguments I hear for designing a system that's high voltage over low voltage is the cost. And that's because a low voltage system will need thicker wires and things like that.
Yep.
And do you have a comment on that kind of cost conceptions on cables, BMS, etc.?
I'd love to address it. At the moment, as of filming this, copper is $10.58 a kilogram. Aluminum is $3.80 a kilogram. And at the moment, I made these two cables as a quick example. This one's 45 grams, and this one's 130 grams. And I simulated two systems, each pulling 100 kilowatts to their motor controller. So in this particular cable, there's 92 cents of copper, and in in this particular comparison on a 100 kilowatt system done at 28S, there is a BMS intrinsic cost of around $40 for cell management, and in the system running this lighter cable, there's a BMS intrinsic cost of around $120 for managing these 96 series cells. And let's say,
and that's just because of the chips that are needed
That's right,
to,
that's the BMS
to be put
chipset.
into series.
So if you have the ability to package your battery near your inverter and your inverter near your motor, then your bus length can approach, this length or shorter even, Let's say that you do a really sloppy job though, which will be tough to pass EM with a big loop area, but let's say you do a sloppy job and you've got 4 feet of cable, I did the math there, and it's $8.63 for 4 feet of cable, for the 28S system doing 100 kilowatts, and it's $2.88 for 4 feet of copper for the 100 kilowatt system at 96S. And so your cost difference in copper between these systems, and again, this is with 4 feet of bus distance, so you just sloppy job packaging, and you've got a $5.75 difference in price in copper to be 28S over 96S, but your BMS cost difference is $120 to $40, so you have around $80 BMS differential, so you're around $70 cheaper, just as this one example in busing, because we talked about how the motor is agnostic to voltage, the battery is agnostic to voltage. The motor controller is sensitive to voltage and operating in these different ranges, and so the cabling difference, in this case with 4 feet of harnessing, it's $5.75 difference that the people are so concerned that I need to save money on making this harness smaller, right? But paying that additional BMS overhead cost, as well as from a safety perspective, everything has to be touch safe for humans, and every maintenance procedure has to be life or death safety critical, in the 96S system.
So it seems like it would have a difference in weight though.
That's right.
Because 4 feet of this wire is going to
Yep.
weigh a lot more. Like this, you said this is 130 grams for about the same
Power.
length
Yep.
as 45 grams, right?
Yep. So there's a difference in weight that, in this case, the differential in weight is, 90 grams between these two, but this is a very short bus distance, right? But
The terminals are large.
In an EV, yeah, the terminals would be a little more massy too. In an EV, your ability to package, for most applications, sometimes you have an aircraft, where you have to put power out a long ways from the battery source, but for most applications, they have a very short distance. And so this difference in mass is only proportional to the length that it has to span.
Right.
So as your difference in packaging height gets tighter, then this mass difference approaches zero, between the systems as your distance approaches zero.
Based on what you're saying about these wires, it sounds like a low voltage system could work for a variety of different applications.
That's right. From high power to low power, depending on how far your energy storage system is from your point of use in your application, low voltage can very likely work for your needs and reduce cost, improve safety and longevity. There's always exceptions where people need to have the battery 100 feet from the motor controller or whatever, their particular weird niche is, and in those situations, low voltage isn't appropriate. But for most situations that we've encountered and dealt with, low voltage would have been appropriate and a cost savings and an advantage in efficiency, performance, cost, safety.
Another one of the major feedbacks I get is regarding charging methods. So I hear a lot of people say, I need a high voltage system because I need quick charging. And I know that here, at least in America, it's very difficult to find low voltage charging. And so without getting into like why charging in America is broken or has opportunity to be fixed, is it true that like you need the higher voltage to charge faster?
Well, it's up to the ampacity of your cabling. From a power electronics perspective at the charger, it really could care less if it's outputting 500 volts or 50 volts. It's how the transformer's magnetics are wound and the size of the bus bar they have leaving the enclosure, right? And obviously the capacitors are different and a few other things, but this is, you're essentially paying per kilowatt of DC charge infrastructure. And so at the moment, there's a lot of infrastructure that only supports, say, 350 amps or so, in which case, if you're say a 100 volt system with 350 amps, you're getting 35 kilowatt charging, which is, not great. It's not the worst, but not great. But if you look at a system like the Tesla supercharger, I know we've measured our own charge current at over 740 amps into that charge connector, at which point that 100 volt system would be, 74 kilowatt charge rate, which is pretty acceptable. It's faster than most companies' existing DC fast charge options, and in that case, it's not a giant connector or a impractical to mate and unmate connector, because that's the exact existing supercharger connector that does 740 amps, and so.
Yeah, absolutely.
The beauty is, though, that existing supercharger connector, it uses a pair, I don't remember if they were 11.5 millimeter or 12 millimeter, but it uses a pair of these Radsock pins, and it's only using one pair of those pins for 740 amps. So let's say you wanted to do a 100 volt system that charged at the same speeds of the Tesla supercharger with 3 pairs of those pins in parallel. You would have a charge connector at that point, which still could package very small. You have 3 little triangles of pins packaged next to each other. You would have higher mate insertion force and extraction force on the connector, and your cable would be stiffer, to manipulate, right? Because your cable would have 3 times cross-sectional area. But in that situation, I feel like it would still work fine. I don't have any trouble bending the existing cables any, right? But
they are pretty thick, though, at the Tesla.
Yeah, they are thick.
Charger.
Many of them have liquid cooling lines too, little hoses. They flow coolant through the cables. But
so wait, are you suggesting a new kind of connector if we were going to build like our dream charge network for a low voltage system?
If I was building, if you could start from scratch with EVs, this would be a great foundation. If you started from a connector capable of, if it was 3 of the Tesla pins, right, that would be 2,500 amps or 2,200 amps, somewhere around there. And at this, at 2,200 amps, a 100 volt system charging a 220 kilowatt charging, which would be, I think anybody thinks that that's reasonable charge rates and reasonable charge times.
You can't even go get a drink at a pit stop and come back without your
car being dead.
Yeah,
at 200
at that
kilowatt
point.
charging. Yep. So that would be a plausible solution for fast charging. Since a lot of existing infrastructure and a lot of existing motor and controller choices were based around essentially 1980s industrial VFD drive technology, which was it's groundbreaking technology to have precise speed control of industrial motors, right? But they ran these voltages based around industry using 480 3-phase and based around the IGBT, having a switching range optimized around, say, 800 volts, 600, 1200 volt spikes, somewhere around there. And so these components
So DC fast charging is very important.
Yeah, definitely. This voltage range, though, that's used today in cars, that voltage range was, selected at a time when you're looking to mount your industrial equipment in different locations in your factory, and maybe your factory has different buildings far away from the pad mount transformer. So if you want to get hundreds of kilowatts or a megawatt from one point to another hundreds of yards away, 480 3-phase is a great option. You can easily carry all the power you need, and long distances with minimal cabling losses, that enabled there to be a bunch of inverter and drive parts and existing high current IGBTs and modules built around this technology for this application. But it doesn't mean that it was ever designed around being a battery powered vehicle application. If it had been from the ground up, every time MOSFET technology gets lower RDS on resistance, the ideal operating voltage for an electric vehicle drops, And so IGBTs, on the other hand, have the same intrinsic forward voltage they've had since the 80s, and it's a property of silicon bandgap conduction, and so it's not going to change, with some new breakthrough. But MOSFETs, on the other hand, every time silicon lithography etching can make finer resolved 3D structures and surface features, then a MOSFET can have higher conductivity per unit area in its die, and this is why we've seen MOSFETs continue to drop in RDS on resistance, improving their current handling per device, while we've seen IGBTs make improvements. Not saying they're stagnant, but they've, obviously no one's even working on beating the forward voltage aspects. There are SiC FETs as well, which is bridging the gap between IGBTs and MOSFETs. They have their own challenges and cost issues as well, though.
Thanks for going really detailed and depth there. I'm sure that's helpful for those that are listening here. As far as cooling methods of the battery, does voltage have anything to do with cooling the battery?
No, actually, it's really interesting, but just the C rate of the pack. So say you've got a 100 kilowatt hour pack in your car. If you discharge at 100 kilowatts, you're burdening your pack at a 1 C rate of discharge load, right? And so whether this 100 kilowatt hour pack was all in one huge series string or whether it was all in one huge parallel group, if you pulled 100 kilowatts off it, it would be identical heat per cell. And when you do high current busing in a battery pack, your errors in current imbalance are magnified, and so your busing design needs to be symmetrically sharing current, some kind of coherent and validated current path that effectively shares, and you validate you don't have busing hotspots, from non-uniform current density.
Totally.
And sometimes they can be difficult to see with your eye too. That's why I definitely run the discharge tests on each prototype module to validate no hotspots.
That kind of leads us into the next point we wanted to make, which is another one of the feedback I get from different people designing battery systems is that everyone is doing high voltage systems, so we need to do it too. And there's kind of a general, I guess, sentiment where I think people are more afraid of high current than high voltage because they think that high current is inherently not safe or more expensive.
A dozen years ago or so, I also had the same misconception, and I wanted to build this is hilarious thinking about it now, I'm almost embarrassed to admit this, but I wanted to build a 600 volt electric bicycle. And with small...
It's like my face in horror a little bit. Yeah.
With small RC hobby packs, it's unfortunately all too possible to just gang them all in series, a bunch of these little 6S packs, 20 volts a piece,
Dang.
Gang up 30 of them in series and you've got yourself a proper mess on your hands. And I would have done it had there been controller technology that was cost effective and sized right, to operate it right. But this was my own misconceptions in thinking, and I had a lot of EE training, but I thought, I squared R and smaller amps numbers equals good, and it's an easy mistake to make. And of course, maybe 25 plus electric bicycles in, now I like to design them around 16S to 20S or so.
So what's the difference, or do you have any experience on what's the difference between taking a high current shock from a high voltage shock?
Okay. Well, essentially, your skin's dielectric value protects you from being able to take high currents when you're at low voltages. And so the only way that your human body can feel a high current shock is by touching high voltage. And that's kind of the paradox. When humans take high currents, like currents that stop their heart and kill them, it's usually in the like 30 to 100 milliamps range. And that's the current that shuts a human down. But the cool news is, again, your skin resistance may vary, right? But, you can touch 120 volts DC, and you feel a path and a tickle, right? And it's maybe uncomfortable tickle, but it's nothing imposing dangerous stress on your heart or respiratory system, Again, that's officially they say don't touch higher than DC. There's something called like the low voltage DC directive or whatever, and it's at 60 volts, where they say it's touch safe below 60 volts. However, they're a little conservative, I think, having touched higher many times, but touching over 200 volts does
it gets a little sketchy.
Usually causes my ribs to displace, and it's extremely uncomfortable. You have tears in your muscles, and usually knocks you down.
That is festive.
Yeah. It's not great.
Yeah. Well, I hope you
it's,
never have to feel that.
It's actually a blessing.
No one ever has to feel that.
Yeah. It's a blessing that you get to take a shock over 200 volts and tell about it, because
I agree.
Only experienced a few of those, and I really
reevaluated
the safety of my current choices on what I was doing after each one. It kind of forces a reevaluation, like reboots your heart and everything. It's pretty uncomfortable.
And that's really the dangers of having a high voltage system. So it's kind of a life safety risk at that point.
There's an insidious danger too, which is that dielectrics break down under electrostatic field stress and time.
Right.
And there's another consideration too. You think about
coatings and things like that in the battery.
Adhesives.
Yeah.
If you don't validate your materials under voltage stress, then you'll get to find out when you build your pack, if they last under voltage stress. A lot of folks will say, well, I measured the resistance, on this adhesive joint, let's say I epoxy down, this cell to a cold plate or whatever. You say, I measure this resistance, it's 100 mega ohms. I'm good. I got 100 mega ohms of resistance, right? And the crazy thing is 100 mega ohms with even 1 volt across 100 mega ohms. It's Avogadro's number of electrons per coulomb that you're multiplying it by. And so you end up, you've got 6.23 times 10 to the 23rd power, I think. And you knock off, with your 100 mega ohms, right? You knock off 9 zeros from that. So you've still got 6 times 10 to the 13th power, hundreds of trillions of electrons every second flowing across your insulator dielectric with just 1 volt across it, right? So when you have high voltage stress across it, and lots of people's isolation isn't even as good as 100 mega ohms. Many people's isolation is like 10 mega ohms, in which case that number of trillions of electrons just got another zero place. But it's this electron flow which drives the breakdown of the dielectrics. It's what carries metal ions through it from the base plates. It's the reason why when you do these tests, you also have to run each polarity. You have to run samples with each polarity orientation between those materials in the interface, because you'll find there's only one polarity that migrates towards a resistive breakdown, and the other polarity will often be stable. And it's because one side's, say, pulling aluminum up through it, and one side's trying to pull nickel off the can down from above, or whatever the particular joint happens to be.
So it sounds like there's a lot of things to consider when designing a high voltage system, as
Definitely.
far as breakdown, corrosion.
There's also
shock.
Let's say that you're going to say 500 to 1,000 volts, then anywhere that you just have a sharp tip the air breaks down spontaneously. You actually split, nitrogen and oxygen into corona plasma just from electrostatic field forces, locally ripping it apart as it crosses these high gradients at the tips of things. And so these make reactive species to break down your plastics, and other dielectrics. But that same stress, even when you don't see it breaking the air down, it's inside your plastic imposing huge stress, or whatever your dielectric, your coating, your insulator. It's inside that material, imposing this stress to drive decomposition with time. That was something I felt the most let down about NE training, actually, was they basically treated dielectrics like, it's something that you polarize to store a static field and a charge in, and it insulates. And they treated the leakage on a dielectric, as something like an unimportant parasitic to ignore, But
polymer science is a really weird one.
Yep.
I'm excited to have Brian and have him chat about
Me too.
all the things that he's learned about.
You could never get all the things he's learned. It would take way too long, but you can get enough to blow your mind in a meeting.
Yes.
Definitely.
So I know that you've been a really long-term proponent for low voltage systems, and that kind of comes from your really intense history throughout batteries and your sharp learning curves that you've had to go through. But I just wanted to make sure I'm asking a more balanced question too and you had mentioned this earlier, if you know any concepts that uses DC high voltage systems successfully, or why you would choose that.
If you have unlimited space, weight, and budget, it can be done safely. It is a lot of extra design cost, parts cost, system cost, and it's probably going to never match the system efficiency that you could have had otherwise. But it can be done, and there are situations where it's the most logical thing to do. But
so if you're trying to beat the Model 3,
what I would love to advocate, though, is that it sure shouldn't be the first place you look to. It should be the last place you look to if for some reason there's some deal breaker that you can't, make fly with lower voltage, because otherwise you're just going to have a safer, longer lasting, more efficient product, and lower cost as well, and less risk to your service technicians, customers, life, first responders in a crash, basically everything gets better. Even bomb cost for the bean counters gets better.
Bean counter.
The trade-offs, are if for some reason you can't locate your energy source proximally to the place you're using the energy. And in that case, then slowly the right amount of BMS cost as those other costs and losses increase, And so also I shouldn't say losses ever have to increase because you're low voltage. If you go to 1/4 the voltage and run 4 times the cross-section cable, you have no losses increase. You have exactly the same losses. And that's why we did these calculations for the difference in copper weight between systems. And
it sounds like low voltage is really just thinking about the future and thinking about what are the kinds of batteries we want to live out there in the wild. As people refurbish them, reuse them, all these wild things that are going to start happening out there.
Yeah, definitely. It's kind of ironic that everybody building high voltage packs, even in cars, builds them in low voltage modules because they don't want to work on it otherwise, and it's safe and effective for your employees to move these things around when they're, say, 60 to 100 volts in these modules, And then they usually don't combine them into this high voltage assembly until it's underneath some kind of, case encapsulating and everything, right? And
it's a huge fire risk to the factory, so you can even look up that happening.
Yeah. Yep. Definitely been plenty of folks learning hard high voltage lessons and corona decay lessons and dielectric decay lessons in volume manufacturing, different companies. I remember, I think it was 2015 or or so that Porsche said they were going to ship the Mission E at 800 volts like the following year in 2015. And then 2016 came and went, and they said it was going to be 2017. 2017 came and went, and they said it was going to be 2018. 2018 came and went, so it was going to be 2019.
What year is it?
They finally shipped the Taycan. The Mission E, I don't think ever shipped. Don't quote me on that.
The Taycan's really nice, though.
Yeah, the Taycan's nice.
Yeah.
I'm just saying, if you want to add something like 5 years of development project delays in learning those ways to make high voltage work, that is an option. Like you mentioned, can you do it? You can do it, but it's certainly not the easy or cost-effective or high longevity route to take.
Yeah, I mean, I even went to go build my own Porsche, and it came out to almost double the price of the Tesla Plaid.
I believe it.
Yeah.
Well, there's some
You're paying
scales.
for craftsmanship.
There's some scales of manufacturing differences. I wouldn't say there's any craftsmanship difference. At least the one that I rode was pretty rough. I think our Tesla had better fit and finish than the one that I drove. But
to each their own.
Yeah, I know which one is a hell of a lot faster. It's our Plaid.
So when it comes to an ideal battery system, now that we've kind of gone through high voltage, low voltage, some perils and some positives, what do you think is the ideal battery system voltage? I know that there's so many different products out there, right?
I'll cover it. If I was going to do a system that was under, say, 2 kilowatts, I really like operating around 24 volts. It's great. I can give you a couple kilowatt system at 24 volts that'll be 98, 99% efficient, in harnessing and power electronics, all the way to your motor, right? So,
and cost effective too.
Yep, and cost effective and touch safe, and anyways, lots of benefits. If the system is, say, in the scooter range, maybe up to, say, 25 kilowatts or so.
Okay.
I really like
a motorcycle.
I really like between 16S to 21S, roughly. One of them gets to take advantage of 80 volt rated MOSFETs, and one of them gets to take advantage of 100 volt rated MOSFETs. And so it's surprising how close in power density and equivalent efficiency all the systems work out to be between, say, 16 all the way to 21S. If you're looking for say
70,
let's say
100.
Yeah, let's say you're looking for up to 250 kilowatts or so, which is great because 250 kilowatts per motor controller, you can run as many motors and or motor controllers as you like. Most vehicles these days are not running a single motor, they're
I know.
running multiple, so it's convenient for low voltage applications to achieve whatever performance level they need. But
Oh yeah, because of the short wiring, right? Because if you're
Yeah.
putting the motor really close
definitely.
to the wheel and everything.
Definitely. But also because each individual, let's say that we have a motor controller, we have that motor controller that does 2,400 phase amps at up to 120 volts. And so this motor controller, per wheel, let's say that you do a 3 motor car or a 4 motor car, like our Plaid's a 3 motor car, but if you do 4 motor car, now you're a low voltage system with 1,000 horsepower, and the 3 motor car, you're 750 horsepower low voltage system, or 500 horsepower 2 motor system, or a 250 horsepower commuter car. Either way, low voltage can fill all of those niches and fill it efficiently and cost effectively.
Let's talk about stationary storage and how we've seen some pretty wild designs come through with very high voltage, like 1,000, 1,200 volts, things like that. Maybe you want to comment on the 48 volt Tesla stationary storage and why that might work compared to...
I personally really like, let's say that you run a bunch of high voltage batteries, you're going to have to deal with balancing resistance in the harnessing, and they're never going to be equidistant from each other, right? Even if you like radial arrays and stuff, it doesn't package well. What Tesla's done is they run just 12S, so 48 volt battery systems max, and each one of these 48 volt systems has its own isolated high voltage DC-DC converter on the back. They output a kilovolt or 1200 volts or something, and because it's an isolated DC-DC, it can share current, and it can also bidirectionally, charge or discharge through this same device. And it allows any system to be isolated. If you have a malfunction in any one of the packs, then it can just stop charging that pack, or discharge it to a low SOC and leave it, not charge it again, without affecting the any more loss to the system than that one, cell in the system. And so I really like it from its current sharing abilities, its intrinsic low voltage safety at each pack that stores energy. And again, the cells themselves, they're just going to hold, if it's 2170, it's going to hold your 18.5 watt hours of energy, no matter how you array it, no matter what the voltages you array it. Just some arrays have higher cost and failure modes and risk associated with them.
Thank you. Is there anything else you'd like to say on battery system voltage on our intro video here?
So when I think about the system that I would personally choose to buy, I would seek out products. If you have two equivalent products and one has a higher voltage system, I would definitely pick the lower voltage of the products, if they're similar function. This is because probabilistically we'll have the least trouble with that one. Obviously if one's designed better or worse than the other, but just from a ways things can go wrong in that system, I would definitely pick the lower voltage option.
Thank you for spending time with us today. We always enjoy hearing your wisdom, and I hope that this has been helpful for you to listen to. And tune in next time. Like and subscribe this video if you're feeling into it, and we'll see you next time.